All right, welcome back once again to the effect. Now, after all of these videos talking about matching, we finally come to the last one, because we've talked about all the different procedures for doing the matching and checking our matching, but I've not really talked about estimation. How do we estimate a treatment effect after we do our matching? Kind of weird to leave that to the end, except that it's relatively simple and straightforward once we've done our matching procedure. Really, once you've done your matching, all you need to do at that point is take your set of matched observations, or perhaps take your weights that you've generated for your weighted matched sample and just calculate the weighted average. Get the weighted average for your treated group, get the weighted average for your control group, and compare those two things, and you're sort of done. That's really all you need to do. When you do that, you can also think about, well, what treatment effect am I getting? Well, if you decided to match the control group to make it look like the treatment group, then you're getting an average treatment on the treated, like we talked about back in the Chapter 10 material. If you do the opposite, if you try to find a treated group that looks as much like the control group as possible, then you'll get the average treatment on the untreated, again, like we talked about in Chapter 10. Or you can get both of those things, the average treatment on the treated and the average treatment on the untreated, and average those together based on the proportion of people who are treated to get the average treatment effect. There are also ways to pick your inverse probability weights in order to get the particular kind of treatment effect average you are hoping to get. That said, that is pretty much it. You're just sort of getting your weighted averages and comparing them between treatment and control, and since you've done your matching already, the resulting comparison that you get should give you the effect of treatment on the outcome. Now, that said, there is still a little bit that we have left out. One big thing that I have not talked about is how to get standard errors. How can we figure out the standard deviation or the sampling distribution of that treatment effect that we have estimated? Now, standard errors with matching are a little bit tough. They're a little bit tougher to do than in regression modeling. And so I would say for the most part, just sort of don't listen to me talk about standard errors and matching. Just sort of pick a particular kind of software that does matching estimation and let it calculate the standard errors for you, because there are a lot of difficult things that go on in these standard error calculations, mostly to do with the fact that the matching procedure itself injects a little bit of uncertainty that you need to account for. So if you just do the comparison, if you regress the outcome on treatment with weights for your matching weights, it will not properly account for all of the uncertainty that went into the matching process, and you will get standard errors that are too small. So generally, just don't try to do the standard errors yourself. Look into the particular software that you might be using and see how they choose to do it. Let them do the heavy lifting. One exception to letting the software calculate the standard errors for you is if you might be interested in doing Bootstrap standard errors. Now, bootstrapping is a process where you sort of randomly get a new sample from your data a whole bunch of times over and over again. And every time you do it, you redo the entire matching process and the entire estimation process, and you get an estimate, and then you do it over and over and over and over again, and you're sort of mimicking the sampling distribution yourself. And because you are redoing your sampling and doing the matching process every single time, it's incorporating the uncertainty of the matching process into your estimate, and therefore you will get the sampling distribution as a whole. You can calculate your own standard errors that way if you feel like it. At least as long as you're doing a weighted approach, doing a process where you are picking samples to either be in the control group or not in the control group, doesn't work quite so well with Bootstrap standard errors. Read the chapter for more technical details on all of that. So we calculated our treatment effect. We've gotten our standard errors either by letting the software do it for us or by calculating Bootstrap standard errors if we're doing a weighted matched procedure. The only thing really left to talk about is how can we incorporate this with regression? Regression comes back once again, because you don't just have to use matching by itself, you can combine it with regression to do some of the things that regression is good at. Let's say you have a research design where you're interested in an interaction term. You want to know how the effect of something varies across different groups. That might be a little bit difficult to do with a weighted average, but you could do it very easily with a regression, and then you just add in your matching weights into your regression, and you are good to go. In fact, I've been talking about this Brookman example with the black legislators in the past couple of videos. In his application, he actually did that. He didn't do just a weighted average with his matching group. He took his matching weights and he applied them to a regression model that had an interaction term with it. We can go one step further even in combining regression and matching approaches to get to what's called a doubly robust estimator. Doubly robust estimator is an estimator that says, hey, wait a minute, when we estimate our matching procedure, there might be some, we might have misspecified our matching procedure, right? We might have picked some of the wrong variables or maybe put them in with the wrong functional form, something like that. But if we do it with regression, we might do the same thing. We might have the wrong functional form. We might have different kinds of matching variables in the wrong place. Maybe we need an interaction term that we didn't include. So we could have misspecified either our model of the matching, which is basically our model of how treatment gets assigned, whether you're treated or not, and we're matching to make those treated and control groups comparable, or our regression model, which is a model of the outcome, right? Our prediction of the outcome, and we have our regression specifying what we think predicts the outcome and in what particular functional form. A doubly robust estimators are estimators that say, hey, you know what? I'm going to make an estimator that's going to give you the right answer as long as at least one of those things is correct. Either I need to make sure that my matching model is correct, or I need to make sure that my outcome model with regression is correct. If one of them is wrong, I don't know necessarily which one, I'm going to be okay. If both of them are wrong, I'm still in trouble. But if only one of them is wrong, I'm good. That's the double robustness part. I can either be correct over here or correct over here, and it's sort of a backup system, right? If one of them fails, the other one will catch me. Now, double robustness is not like the double robust method. Rather, it is a property that certain estimators have. There are a bunch of different estimators that are doubly robust, some of which are harder to do, some of which are easier to do. I'll talk very briefly about one that is relatively easy, called inverse probability weighting with regression adjustment. And the procedure is simple as this. Step number 1, we do our propensity score estimation and get inverse probability weights as we've done before. Step number 2, we use those weights and just take the treated data and estimate our regression model of the outcomes. We apply our regression weights just using the treated data and get a model of sort of what would happen if everybody was treated. Then we do the same thing with the untreated data. We take just the untreated data, apply our matching weights, and then estimate our regression model. So now I predict values for everybody. So I get a predicted value of here's what I predict would happen for you if you were treated while applying those matching weights. And I have a prediction of what would happen for you if you were untreated based on those matching weights. And I compare those two, and that gives me my estimate of treatment, comparing what I predict everybody would be if they were treated against what I predict everybody would be if they were untreated. And so I get my inverse probability weighting in there for matching. I get my regression adjustment in there because I'm estimating a regression model both for the treated group and the untreated group, and I compare them to get a treatment effect. And this estimation procedure is doubly robust. If I've made a specification error in my propensity score estimation, then as long as my regression model is good, I'm good to go. If I make an error in specifying my regression model, then as long as my inverse probability weighting model was specified properly, I'm good to go. I don't necessarily know which one of them succeeded, but as long as one of them did, I'm fine. All right, that closes us out on the matching chapter with some ways of estimating treatment effects once we've done our whole matching procedure, where all the sort of difficult questions are. The actual estimation is quite a lot simpler. So that is it for matching. Thank you very much.